Hello and welcome. My name is Ammar Jessa, and in this video I will be presenting my thesis titled Low Reynolds Number Scaling Effects for Small-Scale Rotors as a partial fulfillment of the requirements for the degree of Masters of Applied Science in Aerospace Engineering. To start off, I will be talking about the motivation behind this thesis and what the problem was that I was trying to address. So currently there has been quite an increase in the popularity of small unmanned aerial vehicles, particularly multi-rotor vehicles, in various industries such as real estate, construction, the military, and aerial photography. This is due to the abilities of these vehicles to vertically take off and land, hover in a fixed location, and maneuver in confined spaces. This allows these vehicles to go to places where humans and other larger vehicles cannot. One of the main requirements for these vehicles is performance, more specifically efficiency and the ability to use less power in order to stay airborne for a longer period of time, all while remaining as lightweight as possible. And one of the main aspects of the small unmanned aerial vehicle that influences the performance is the rotors. This makes rotor selection and design a very important part of the initial conceptual design stage. When designing or choosing a rotor, there are many aspects to consider, such as the various flight speeds that the vehicle will be encountering, the motor RPM, the size of the actual vehicle, and the size of the rotor blades themselves. Generally, the forces and moments produced by the rotors are non-dimensionalized and put into coefficient form in order to directly compare between different sized rotors. An issue that presents itself is at low Reynolds numbers around 100,000. At this Reynolds number range, the viscous effects are more dominant and pose difficulties in using the standard coefficient-based method to scale between rotors of different sizes. From previous research done on airfoils, it is known that at low Reynolds numbers, the maximum coefficient of lift is reduced and the minimum coefficient of drag increases due to these viscous effects. The thrust and power of a rotor are dependent on the lift and drag respectively, and so the efficiency of a rotor is influenced by the Reynolds number. Overall, in essence, the scalability between rotors of different sizes is an issue at lower Reynolds numbers. Addressing the scalability issue was the objective of a thesis, more specifically verifying the existing relationships between rotor size, forces, moments, and Reynolds numbers, and explore their limitations in the low Reynolds number regime. This was done by experimentally wind tunnel testing various sized rotor blades at different Reynolds numbers and advance ratios. These experimental results were also compared to a computational method based off the blade element momentum theory. Before explaining the results, an understanding of the aerodynamics that govern rotors is needed. The first aspect to consider is the local reference frame that was used, which is shown as a top-down view of the rotor disc. The rotor disc is the plane that is created by the tip of the rotor blade as it rotates around a full revolution. The angle of the rotor disc relative to the incoming free stream velocity is known as the angle of attack. All the tests run in this thesis were done at a 0-degree angle of attack, also known as fully edgewise flow. The position of the blade within the rotor disc is defined as the azimuth angle. So for example, here at the trailing edge, the azimuth angle is 0 degrees, and on the advancing side, the azimuth angle is 90 degrees, and so on. An important variable that was used in this thesis was the advance ratio, which is the ratio of the free stream velocity to the tip speed of the blade, and basically defines the forward speed of the rotor. Another variable that was used in this thesis was the Reynolds number, which is a ratio of the inertial forces in the fluid to the viscous forces in the fluid, and governs whether the flow is laminar or turbulent. The Reynolds number is used as a similarity parameter for viscosity to scale objects in a flow. The forces and moments that were recorded were non-dimensionalized as shown in this table in order to compare between the different sized rotors. So for example, you can see for the force was non-dimensionalized using the air density, the rotor disc area, the rotational velocity squared, and the radius squared. The moment was non-dimensionalized in a very similar way by the air density, the rotor disc area, the rotational velocity squared, and in this case, the radius cubed as opposed to the radius squared that was used for the forces. All the forces and moments in this thesis were non-dimensionalized using these equations here. The forces and moments that were recorded were a function of the azimuth location of the blade within the rotor disc. First, I will talk about the effects caused by the advancing and retreating blades. On the advancing blade, as shown here on the figure on the right, the free stream velocity is added to the tangential velocity, causing an increase in the total resultant velocity and an increase in the effective angle of attack. On the retreating blade, as shown here on the figure on the left, the free stream velocity is subtracted from the tangential velocity, causing a decrease in the total resultant velocity and a decrease in the effective angle of attack. This velocity differential results in more lift being produced on the advancing blade than the retreating blade, causing an imbalance that results in a rolling moment to the left about the longitudinal x-axis. The blade profile drag is also higher on the advancing side due to this velocity differential, resulting in a net drag force on the rotor disc acting rearwards. The leading and trailing edges of the rotor disc are affected by the skewed inflow conditions caused by the wake. In forward flight, the rotor wake is skewed rearwards and causes an increase in the downwash at the trailing edge and a reduction in downwash at the leading edge of the rotor disc. As you can see here for the trailing edge on the figure on the right, the increase in axial velocity causes a reduction in the effective angle of attack, while on the leading edge, as shown here on the figure on the left, the decrease in axial velocity causes an increase in the effective angle of attack. This differential in the effective angle of attack results in more lift being produced at the leading edge than at the trailing edge, causing an imbalance that results in a positive pitch-up moment about the lateral y-axis. The blade profile drag is also higher at the leading edge due to the higher effective angle of attack, resulting in a net side force on the rotor disc acting towards the right. With an understanding of the aerodynamics governing the rotors, the experiment can now be explained. For the experimental tests, 3 T-motor series rotor blades with diameters of 12 inches, 15 inches, and 18 inches were tested. The figure here on the right shows the 3 rotor blades. Despite being different sizes, all 3 rotor blades had the same chord and twist distribution, allowing them to be directly compared. The table on the left here shows a test matrix of the tests conducted. Each of these rotors was tested at 3 different chord Reynolds numbers, 39,000, 78,000, and 117,000. This chord Reynolds number was based on the chord length and tangential speed at 75% of the radial location of the respective blades. So for example, on the 18-inch blade, it was somewhere about here. To compare between the different sized rotors, the chord Reynolds number at 75% of the radius was kept constant by changing the rotor RPM as rotor diameter was changed. So for example, for the 12-inch rotor diameter, to achieve a Reynolds number of 39,000, an RPM of 2,256 was required. For the 15-inch rotor, to achieve the same Reynolds number of 39,000, a rotor RPM of 1,436 was required, and for the same Reynolds number for the 18-inch rotor diameter, RPM of 1,000 was required. For a given test, the rotor RPM was held constant while the advance ratio was varied by changing the tunnel velocity and therefore the free stream velocity. For each test, the target motor RPM was set and held with a PID controller for 30 seconds, during which the forces and moments were recorded. The tunnel velocity was then increased in increments, with the forces and moments produced by the rotor blades being recorded at every increment. The equipment used for the wind tunnel test is outlined in this slide. The rotor blades used in these tests were attached to the rotor mount that is shown here. The Scorpion motor attached to it was controlled by an electronic speed controller that was attached to the power supply and the data acquisition system, and was responsible for spinning the rotor blade. An RM22 rotary magnetic encoder was used to measure the RPM of the Scorpion motor shaft. The motor RPM was held constant by using a PID controller that took the RPM input from the encoder and adjusted the RPM output through the electronic speed controller back to the Scorpion motor. The Mini 45 FT sensor shown here measured all the forces and moments developed by the rotor. The outer cowling enclosed the electronics and streamlined the test section to reduce unwanted aerodynamic effects. Additionally, all the wires from the electronics were routed through the shaft of the actual test stand, once again to reduce any unwanted aerodynamic effects. The test stand assembly is shown here on the figure on the right, attached to a turntable that had the ability to rotate and change the rotor angle of attack. However, in this thesis, all the rotor tests were run at a 0-degree angle of attack. In the next few slides, the results for the experimental tests are presented. Only the results for the thrust coefficient and the pitching moment coefficient will be shown, as the data for these two coefficients showed the two types of results that were observed. In this slide, the plots for the thrust coefficient versus the advance ratio are shown for a Reynolds number of 39,000, 78,000, and 117,000. Looking at these plots, it can be seen that the thrust coefficient increases as advance ratio is increased for all three rotor diameters and all three Reynolds numbers. Observing the first plot, which corresponds to a Reynolds number of 39,000, it can be seen that there is some scatter between the data points of the different diameters, and that scatter stays consistent throughout the full range of advance ratios. Looking at the plots for the Reynolds number of 78,000 and 117,000, it can be seen that as the Reynolds number is increased, the scatter between the data decreases, and the data points for all three rotor diameters line up. And this can be seen in the maximal case, looking at the Reynolds number of 117,000, where the data points for the different rotor diameters line up. There are a few points to note here. It can be seen that as the Reynolds number was increased, higher advance ratios were not achievable. This is due to the fact that as the rotor RPM, and therefore the core's Reynolds number, was increased, higher advance ratios were not achievable due to wind tunnel speed limitations. Another point to note is the results for the 12-inch rotor at the Reynolds number of 117,000 are not included in the results, as there were vibratory effects observed while maintaining a rotor RPM corresponding to this Reynolds number. In this slide, the plots for the pitching moment coefficient versus advance ratio are shown for a Reynolds number of 39,000, 78,000, and 117,000. Looking at the first plot, corresponding to a Reynolds number of 39,000, it can be seen that the pitching moment coefficient shows no clear trend as advance ratio increases for all three rotor diameters. Additionally, there is substantially more scatter between the data points of the different diameters as compared to the thrust coefficient on the previous slide. Additionally, the scatter also increases as advance ratio increases. From the second plot, corresponding to a Reynolds number of 78,000, a slight trend can be seen between all three rotor diameters. However, no concrete trend can still be observed. The scatter between the different rotor diameters is still evident. For the plot of a Reynolds number of 117,000, a trend can now be seen that shows an increase in the pitching moment coefficient followed by a very gradual decline as the advance ratio is increased. Additionally, the scatter between the different diameters has decreased and the data points now line up. From the plots of the thrust coefficient on the previous slide and the pitching moment coefficient on this slide, it was seen that as Reynolds number was increased, the variation in the data between the different rotor diameters also decreased. This was observed for all the other coefficients that were recorded in this thesis as well. In essence, this shows that the coefficient-based method is pretty accurate and can be used at higher Reynolds numbers, which in this case would be 100,000 and above. The experimental results from the wind tunnel test were compared to a computational prediction method based off the blade element momentum theory. The prediction method combines the blade element theory with the momentum theory. The momentum theory shown in the bottom figure here treats the rotor as an infinitesimally thin actuator disc that induces a fluid velocity through it by means of a pressure jump across the disc. The momentum theory was used to find the inflow velocities across the rotor disc. Blade element theory, shown here in the upper figure, is used to determine the forces developed by the blade elements based on the inflow conditions determined using momentum theory. In the blade element theory, the rotor blade is represented using a collection of two-dimensional elements which are radially distributed. The performance of each of these elements is independent of the adjacent elements and is modeled as a two-dimensional airfoil section. The blade element forces include lift and drag, which also includes the profile and induced drag. Adding the blade forces across the blade radius leads to the rotor forces and moments once averaged over a full rotation. To determine the airfoil section aerodynamic characteristics, a table lookup scheme was used. The tables consisted of a sectional aerodynamic coefficients that were generated using experimental and 2D prediction methods such as Xfoil. The computational method took in inputs for the angle of attack and Reynolds number, and using these input variables, the table lookup scheme was executed and the sectional aerodynamic characteristics were found, which were then used to find the rotor forces and moments over the full rotor disc. The computational method also incorporated a linear inflow model for forward flight. In forward flight, the rotor wake is swept backwards and is strongly dominated by the presence of tip vortices, and therefore uniform inflow is no longer valid. Modeling the wake in forward flight is extremely complex, and so linear inflow models are used which can estimate the induced velocity without having to explicitly model the wake. As can be seen here on the figure on the left, the wake is skewed back at a given skew angle from the vertical in forward flight. Experimental research of the inflow over the rotor disc in forward flight has shown that the longitudinal and lateral variations in the inflow are linear. The Pitt and Peters linear inflow model, whose physical depiction is shown here on the figure on the right side, was used in this program to model the inflow in forward flight, as it provided the best agreement with experimental observations. So looking at the graphic here, the trailing edge is denoted by an azimuth angle of 0 degrees, and the leading edge is denoted by an azimuth angle of 180 degrees. As you can see, at the trailing edge there is a larger downwash, and at the leading edge there is a slight upwash. There is also a lateral variation in the inflow caused by this skewed wake, and you can see on the advancing side at an azimuth angle of 90 degrees there's a smaller downwash, while on the retreating side at an azimuth angle of 270 degrees there is a larger downwash. The next two slides present the BMT predictions with the experimental values for the thrust and pitching moment coefficients. This slide presents the predicted and experimental results for the thrust coefficient versus the advance ratio for the three Reynolds numbers of 39,000, 78,000, and 117,000. Observing the first plot corresponding to a Reynolds number of 39,000, it is seen that the prediction underestimates the experimental results for the thrust coefficient for the full range of advance ratios. Looking at the plots for the Reynolds numbers of 78,000 and 117,000, it is seen that the prediction shows a very good agreement with the experimental results. As the Reynolds number was increased, the predicted and experimental data showed a greater agreement, which was also seen for most of the other coefficients tested in this thesis, except for the pitching moment coefficient. This slide presents the predicted and experimental results for the pitching moment coefficient versus the advance ratio for the three Reynolds numbers of 39,000, 78,000, and 117,000. Observing all three plots on this slide, it can be seen that the prediction underestimates the pitching moment coefficient for all three Reynolds numbers tested. Additionally, the predicted trends for the pitching moment coefficient also do not agree with the experimental results for all three Reynolds numbers. However, some slight similarities in the trends can be seen at lower advance ratios for the Reynolds number of 78,000 and the Reynolds number of 117,000. In conclusion, experimental and computational tests were conducted to verify relationships between rotor sizes, forces, moments, and Reynolds number in the low Reynolds number regime. From the experimental results, it was seen that the conventional scaling laws work well at higher Reynolds numbers above approximately 100,000. At low Reynolds numbers, there were variations seen between the different rotor sizes, particularly for the pitching moment coefficient. The computational prediction method also showed good agreement at higher Reynolds numbers for most coefficients, except for the pitching moment. Overall, from the results obtained in this thesis, for a Reynolds number above approximately 100,000, the coefficient-based method can be used to directly scale between different rotor sizes with the same chord and twist distribution with a high level of confidence. Additionally, The prediction method can also be used to obtain the coefficients for the different rotors above this same Reynolds number. Thank you.